Excellent. So I was thinking about some of the common themes that have emerged out of the presentations. And in some way, this kind of reflects the challenges of the area, which is it's just almost too big even to get our hands around. I mean, you know, there were plenty of common touch points, but also a lot of diversity. But one of the things that I thought came up pretty clearly was the move, or at least the interest in moving, or the need to move toward more sort of real-time analysis. You know, not only in a predictive sense, but just in a kind of rapid reaction or quick turnaround sense. And I wondered if I'd like to go down the table and ask each of you to comment on a little bit on that aspect. So, Niall, perhaps you'd like to
me first,
start.
I've been drinking. Real-time analysis is forced. The statistician in me wants to say, I'd always prefer not to do that. Can you hear me? Real-time analysis, sometimes it's needed, sometimes it's not. It's a little like the commentary about putting the computation on the device rather than collecting data. Sometimes you need to do it, sometimes you don't. Real-time analysis is very difficult simply because you have to adapt to a changing world. I have colleagues who are setting up businesses claiming to sell sophisticated data mining tools that will do analysis on data in motion. There are kind of deep theoretical issues to solve before such algorithms can be made reliable.
Thanks. I think what we're sort of seeing in our work is that the increased importance of speed over accuracy, which is really quite a difficult concept for, you know, I guess against the sort of background about how a lot of us have learned, you know, what right and wrong is. And it really, you know, it's, I think across business, let's say, you know, I think there's a lot of difference between the importance of speed over accuracy on, I don't know, a commercial website versus presumably an airline engine. So I think that's a really, you know, both are going to remain important. I mean, definitely for us, you know, there is a consumer expectation to be able to do things kind of in real time, and there's lots of experiences now that people are getting where they're getting stuff in real time, kind of the blink of an eye, and so increasingly a lot of businesses are looking for computation that's done in real time, and we're expecting that this will kind of be done in a way where we'll do, say, daily modeling and then put a kind of real-time filter on it or change to the model and try and get the best of both worlds. But it's definitely a really sort of hot topic for us is how to do yeah, what appear to be complicated analytics, but do them in you know, 200 milliseconds, that kind of thing.
I mean, a lot of our work around personal data is with the dreaded Internet of Things that's coming, and if you list through all the applications that people, you know, come up with, the classic one is looking after an aging population in their own home, and the question is, you know, there's a lot of that data. Again, we're into the category of most of the data is boring, and it's the anomaly detection, and it's relating to, you know, and I was talking about network intrusion detection. There are some things that I think we will need to, but to me they tend to fall in the category more of where the anomalies happening, right. Such as you can take some action, which may involve simply, you know, the communication to it. I mean, again, it gets back to this issue of the angle I'm approaching it from is the privacy angle, which is the last thing we need is constant reports of where someone is in their house, and they've gone to the bathroom and they've done that. I mean, I don't want to. Well, unfortunately, my mother died before Christmas, so it's not a good topic. But we don't want to be monitoring each other like that. You want to know when something strange happens, and then you want the person to be involved in communicating that as well. So I come at this from a very particular point of view, because a lot of our stuff is around personal information as it gets into our very personal lives. And there's a lot of things where we really do want the real time, because it will give us all sorts of useful applications and assurances, but that's to be tinged with this issue of how do we maintain the privacy. And that, to me, then, is the challenge of how do we do those analytics in isolation in a highly distributed way because of that.
So, just as an aside, one of the things I've heard is what will soon dictate the time it takes aircraft to turn around at airports is the time it takes to load the information system, the entertainment system. That will be the pacing item for aircraft in the time. But to the question, for us, it's probably a stone-cold commercial decision. These things cost money, and they cost big money to put these in place. So we certainly need them. It's an expensive product, hugely expensive. So anomaly detection, we definitely do. For us, real time, we do. We will do more, but again, it will always be a commercial balance. Can we? What's the cost benefit analysis of it?
Yeah, interesting. Great. So let me go ahead and open up the floor to questions on any of the things we just heard about, or anything you'd like to ask our team of speakers. So go ahead. Yes.
So I was just wondering, because a couple of you alluded to it, what do you think the best solutions are to the problems of pathological statistics, where I would define pathological statistics as non-stationary, or some of you said explicitly low signal, even though it's low signal, not high ID. I mean, in that scenario, you can collect all the data you want as well. It doesn't necessarily tell you everything.
I'll take that as I'll go back to my history. Okay. So for many years I did networking, particularly ATM networking, and there's a whole thing there about looking at flows of packets and networks to try to predict quality of service. And the issue always was, every time a new application comes in, or every time a patch is done for an application, the statistics of the data change. The question, and the way we approached it, was to say, what is the time window over which we wish to predict? And how much data do we need to measure in order to make that prediction? So, for example, for quality of service, and indeed there was a startup in Ireland that came out of the Dublin Institute of Advanced Studies that did this. Basically, if you wanted to predict the next half hour, the last 5 minutes was fine. And the fact you just had to keep remeasuring it and saying, this is a sufficiently good predictor for the next half hour of what's going to happen. And you just kept recalculating it. And that worked very, very effectively. I ended up Cisco buying the company and putting it into their Quast product. So accepting the fact that it was non-stationary, asking the question of over what time frame can you do sufficient measurement to predict the future, understanding that that data is going to become irrelevant in 2 days' time. So that was one solution we had back then. That's 10 years ago.
So, say a bit more about what you mean by pathological.
So I guess part of my background, for example, is biology, so there's plenty of statistics in biology which are difficult to model. Notably, you mentioned it, neuroscience, because you can have quantities which vary a lot irregularly, not necessarily in stable distribution. And then if you add into that multiple modalities of information, which is also in medical, you end up with a problem that if you just take, for example, to be simple, frequency statistics becomes actually a close. And yeah, I know people are trying to solve this problem, and I'm just wondering what you thought about, especially what you were describing. So actually, I think maybe one of the most sensible solutions is you have something that's dynamically altering the solver. I'm sorry whether one can actually do better than that. How it might work.
So, I don't want to talk about stationarity or things like that. To some extent, you have to hope that the present is like the past, right? It's very easy to contrive a process that is unpredictable mathematically. A problem that the big data enterprise has is that you can collect any kind of data. And the only way you can ever determine if it's got signal in, well, is to go and find it, and endless resource can be thrown at trying to extract signal when none's present. I don't see a solution. Which is good news, right?
Well, the only, so just a passing comment as people thought, I think that there are systems that do software, and I think we are one example of those systems. I mean, an organism, you could just say that the organism we do big data. I mean, an organism is in a situation which is not entirely, sometimes statistically not well founded. Sometimes things only happen to you once in your life, and yet we function.
Okay.
Deep. Next question. Yes, in the back. Yeah.
Yeah, I was referring to, I want to refer to the example of Derek provided around smart meters and data privacy. And of course, there are, I work at UCLA, it's obviously an area of interest to us, and data privacy is a big issue, something that the Department of Energy is trying to take very seriously. But I guess my concern is that we focus too much on what is theoretically possible in terms of, in the smart meter example, someone hacking into the system, looking at the patterns of heating or showers or whatever it is, trying to determine whether someone's at home or not, and then Daily Mail headlines are going to break into your house and steal all the goods. When the reality is, you need to be a computer science expert to hack the system in the first place. You need to be an energy analytics expert to understand the patterns of energy use, and then you've got to go around to the house and make the average worth of street value of goods sold about 50 clicks. So it's not a great business, even for the lowest grade criminals. So I guess my question is, how do we balance that engagement around data privacy between what's theoretically possible and what's pragmatically possible or likely?
Great question.
Well, I mean, I'd start with what is it you want to achieve with the data, and simply ask yourself the question, can you do it using privacy by design? So can you design it to be private and have done with it? So right now, and I diss a lot of my colleagues like this, right now we're being very lazy in saying, well, we'll move all the data somewhere and then we'll do the analytics on it. And we're not asking the question, well, really what we want to do, and can we design it privately? And pretty soon, as in next year, no matter what happens and whether we have a UKIP Conservative coalition that takes us out of Europe, Europe at least is going to mandate that privacy by design is in systems, at which point you will be having people standing up and saying, you must do it this way. I'm an optimist, though. I think we can design these systems to be private. You just got to think harder about it. So we can do that. Now, if we want to get into the hacker scenario, the actual concern I have is less so the petty crime than what happened in Spain, for example, was a systematic attack on 10% of the smart meters that have been installed, which, perpetrated by a foreign power, would be considered, a terrorist act. If you take out 10% of the homes in the UK, all at once, instantaneously, generators will pop off mounts. It will do untold damage. Never mind, the government will fall. So there's a real cybersecurity issue around what we do with the implementation of these systems. And again, the excessive reliance on centralization of this, such that there's one point of attack, it's a honeypot for the hackers. So I think there's a systems level thinking that needs to go into this that I'm not sure has necessarily run its course yet. I'm not saying people haven't thought about some of them, but I still think there's a lot of discussion to be had about exactly how these systems should be instrumented, built in the future and architected, so that it's privacy and security. It's not just, we can't just say, well, let's not concern ourselves with the privacy, because with the mechanisms to ensure privacy come lots of mechanisms to ensure security. So cybersecurity starts at home.
Good point. Anyone else want to add to that?
I think there's just I mean, on all these things, I think there's something to be said that not assuming that all people want the same stuff. You know, among the billions of people in the world, there are some who really, you know, will want to keep absolutely everything to themselves, and there are probably equally numbers who are very happy for the right exchange to, you know, I think there was a comment of, you know, people using Gmail, and I think, yes, you know, and it is quite a scary thought that, you know, the Google computers read all of your Gmail in order to advertise to you, but it is also an absolutely amazing resource to have for nothing. And, you know, likewise, you know, I'm sure most of us in this room are happy that for Google or whoever to know our location in order to give us, you know, sat-nav. We might be a bit more dubious if it's Angry Birds who want to know our location for some, you know, odd reason. You know, that. So ultimately, I think it's around.
It does ask for it.
Yeah, no, I mean, it's crack, isn't it? Ultimately, it's about how do you make sure that you don't get caught into a trap of, you know, assuming that you have to provide one service for everybody, and for every, you know, more or less for every person who's really concerned about how much information there's giving away, there's equally as many who are really, you know, gasping for why can't this be connected to this in order to give me a better service, and, you know, so I think there's a real sort of, you know, realize that different people have sort of different levels of happiness and expectation, and really not worry about sort of only going to the you know, lowest common factor, but actually seeing that different people want different things or are happy with different things.
I think that's true not only at the individual level, but also kind of an aggregate. I mean, if you think about how much more efficiently the government could implement the census using other types of data that the government already collects, it seems, you know, very, very clear that there are advantages there. But at the same time, we don't even really have certainly don't have the legal frameworks in place yet to think about how to aggregate and cross-correlate. You know, even when there's one owner, potentially the government. But so it's not even at not only at an individual level, but I think you see the same thing at the organizational level as well. So it's very interesting. Yes. Oh, I'm sorry. Go ahead.
Well, my experience with big data is that it's a big deal. Basically, people just use blanket tools to collect data, and they use it for all possible circumstances, and you end up having more gaps or errors than it's actually worth. So it's not big data, it's a big gap. And in my opinion, the reason is that the data analyst is not data only. Maybe, and I'm annoyed by not being able to do proper statistics because I keep thinking that from any sort of experiences, or I don't know, maybe.
Can you contrive a scenario where the analyst would also be the owner?
I think Rolls-Royce would be a strong example.
Which,
Right?
I mean, I was just thinking this with one of the earlier questions is, it might be a bit provocative, but the assumption that the person owned the share example, why is that data owned by the individual? Why is the data could be owned by the energy company, it could be owned by the manufacturer of the device. Yeah. And that's one of the issues we face is, whose data is it? Is it our data? Is it the airline's data? Is it the airframer's data? To some extent, if we're tracking what movies people are watching, or we don't, but if someone's tracking what movies people are watching when they're on board, right, that's personal data. Is that personal data? Is that airline data? Is that the engine, the entertainment management systems data? So it's not always clear whose data it is. Yeah. And for us, potentially there's big commercial advantages in having ownership of data. So I think that's why people want the data. Yeah.
So this is where I make a rather boring, but unfortunately legally true statement. Data is not owned. There is no law, no concept of ownership. If you have data, you can keep it private. You not show it to other people. If it concerns an individual, there are obligations you have if you process it. But data is facts, and facts cannot have, unless it's associated with the representation of copyright work. So there is a very complex legal situation around this that makes it very difficult to operate. And we often, I myself, often fall into the habit of saying, it's my data. And it's like, well, it's not my data. It is simply a set of facts. But when it comes to personal data, there are legal requirements as to how it is processed and things like that. It's an interesting one because I know that manufacturer of that very large truck views that that's their data and doesn't belong to the people who own the truck. Because, of course, it's designed to fail at exactly 25,000 hours when the warranty runs out. If the owner of the truck actually had the data, they might be able to know which ones they could extend to 30,000 hours, and they would save themselves a bucket load of money. And you'll be in the same situation. So the restriction of access to the data. But if I get hold of some of your engine data, you can't demand it back because it's not an owned thing. And it's actually a very complex issue when you get down to it. So.
It's a very interesting point.
It should be treated as a commodity. You own a commodity that you sell, and if you don't do it, such a quality, you get analysis.
I think in some ways.
So
Yeah.
commodity, as commonly used, means that I'll sell it for $5 and you can sell it on everything else. And one of the key problems with personal data is that the receiver of the data sets, basically, the context in which it is being shared sets the value. And so if I give it to you and you use it for some other purpose, it's not a commodity. Because my health record, depending on what the content is valuable in different ways to different people. So if I have a very rare gene sequence, it's of enormous value to a pharma company, but it's of zero value to Coke. So if I sell it to Coke for $0 for free Cokes or something, or sell to Gmail for free email, the fact that they can make hundreds of thousands by selling it on. So there's a reason. So unfortunately, don't get me started on personal data because I'll be here all day. But there is again that issue of the contextualization of the data and who's receiving it actually sets the value. So it literally can't be referred to as a commodity because it's. Now, one of the problems is that many entities are trying to treat it as a commodity today. That's what the data brokers do in the US, and the few men are hitting the fan because of that.
Interesting point. I know there was another question. Yes, please, go ahead.
So I work in that work, and I often hear from our customers in the industry that there's a skills gap for data science. I wondered whether the panel agreed with that observation, and if so, what can we do about it?
It's a great question. Yeah. Anybody want to take a go at this one?
What is a data scientist? We can't talk about there being a gap until we can define what a data scientist is, right? I'm kind of cynical by nature.
We hadn't noticed.
Much of the data science hype is marketing. I showed you a slide earlier where, in future, data scientists will have degrees in anthropology and art history. Right? I find that unbelievably stupid. There's probably a gap. You're MATLAB, right?
Yeah.
So the people who would use MATLAB in like cloud-like scenarios, for example, they're probably that you either go for computer science kids, it's terrible. You recruit graduates from computer science who are good at programming and understanding the computing infrastructure, or you recruit graduates from maths or stats, physics, who are sort of good at this sort of inferential aspect. If there's a gap, it's because you need somebody who can do both.
I think that's right, and I think it's fair to talk about a gap in terms of the skills that might be looked for to solve some of these problems don't necessarily lay up against any one field, and the intersection of computer science and statistics is a very natural place where you start to see that. And I mean, we struggle with this in our curriculum design and our training programs because one cannot simply add more. One has to, for everything that one adds, one must also cut something. So if you look around at what's being done, so Berkeley was an early offerer in the US of masters in data science. Warwick is doing an undergraduate degree in data science in the UK. the quickest way to turn around a data science program is to look through your current course catalog and pick half the stuff from computer, drop half of a computer science degree and drop half of a statistics degree. And I think there's a need for those types of skills to be taught, but I don't think within the education sector that we've really exactly worked out how we haven't really planned for that. We've more kind of moved quickly to kind of try to meet the pull from industry. And I think, over the next several years, we should see better design of these things, but it's going to take a little bit of time for us to get there. Comment or question?
Quickly off the back of that, I find in practice that statisticians and computer scientists can't communicate enough on positions to work together. Do we need
maths kids are very famous for yes.
At least you're in the room.
Yes.
Yeah.
But again, that sort of this comment from the educational perspective, we're there to train on technical stuff. The fact that you know the difference between a shy mathematician and a confident mathematician, right? Yeah, the shy mathematician looks at his feet when he's talking to you. The confident one looks at yours. Giving interpersonal skills, communication skills is something I think is probably off syllabus for us.
Yeah. No, I think that's fair, and I think there's also a specific application expertise component as well. I mean, it goes back to your point about the data analyst not being the data owner. I mean, if we forget about the word owner for a second, but the data analyst might not be somebody who has any conception or understanding of how the data were generated, et cetera, et cetera. And I think that's also part of the issue. But yeah,
so maths and computer scientists actually are pretty close to each other in terms of personality types. I run a research lab where psychologists and design and linguists, as well as computer scientists. And the only way it works is we've put them in the same room for 5 years. In order to do research on some of these complex topics, we need people with PhDs in the subjects, and then they need to talk to each other. And we've been on a 5-year journey to build that. It's not a quick thing to do. So I'll plug our data science course. We did exactly what you did, cut and shut, and a stats degree and a computer science degree, and get them out the door, and they can do a bit of both. But at the end of the day, these challenges, and especially the research challenges, need people with PhDs in each of these fields, and you've just got to put the teams together. Yeah. And the way those teams start working effectively is after a year or two, they actually can communicate with each other. But it's not a quick job, and it's not something that happens by saying, we'll all stay in our departments and we'll meet once a week for a meeting about the project. It's by every day living in each other's pockets and talking to each other all the time. So I think it's something that at the research level we can do, by putting together research groups that are interdisciplinary and leaving them alone for long enough that they actually get to know each other. But that's a human challenge. It's not a...
That's a good point. I'm conscious of the fact that we've got a sort of reception and networking time until 6 that I don't want to cut into too strongly. But on the other hand, I think we have time for one or two more questions because I think it's great to have everybody sitting up here and giving of their expertise. So any more questions? 1 or 2 more questions? Anybody? Yeah, go ahead.
This might have been a question for the first session, by the second as well here for the last. On the subject of model selection, said quantity-statistics isn't really useful on large data sets with dimensionality. Obviously, Bayesian statistics is issued with subjectivity. And I've come across another sort of foundation of statistics and information around basically formalization of raising minimum description length statistics. Has anyone on the panel run into this, and does anyone have a resounding criticism? Because obviously I can't trust the papers on it.
So, from my view, is that minimum description length is a reworking of Bayesian inference, personally. But I'm not here to propagate it. If I was, then naturally I'd say it had something, but I actually feel it's essentially all the same construction as a Bayesian argument, but it's sort of worked backwards.
I mean, one thing we do know is that pure frequentist-based analyses start to fail in high dimension, or when the number of parameters in the problem begins to be on a similar order to the amount of data. So usually we handle that by some kind of regularization, and MDL is one way to think about it. The Bayesian formalism is another way to think about it. If people who like to stay frequentist tend to pick up other explicit penalty terms. So I think it's related, but you have hit on an important point, which is that basically one cannot draw inference from a single observation, and one cannot infer n variables from n observations. And so in these situations where the data sizes are large, but the complexity is also very high, one needs some form of complexity control. And I think everyone has their own personal favorite way to think about it, but I think one way or another, complexity control ends up featuring in almost all of modern high-dimensional statistics. And it was present in the talks this morning, and all of you here are very, very welcome to join for the next couple days if you'd like. I'm sure somebody's going to, the fire marshal people are going to kill me for saying that, but there'll be sort of 2 more days of talks in that direction, and I think you probably wouldn't see a single talk that doesn't feature some kind of model complexity control, because it's very necessary in these contexts. That's at least from a theoretical side, but others may have things to add from a practical point of view.
One thing about that is a bit like, don't you know that reduction of complexity, so basically you just check the complexity of the model. And it's a similar kind of flavor of thing where you try and penalize the complexity of the model in order to make sure the model is actually descriptive, which is an approach that often then you find that the models are just much more low dimensional. You have to, in the end, make some assumptions about what you're doing.
Yeah.
The other
Or you don't do it.
is whether it all feeds up from channel source.
You mean channels? So really, it's actually more related to Kolmogorov.
Yes, yeah.
But that's not something you can actually algorithmically solve. It's known to be. So ergo, you get the
In your model set.
yeah, you have basic assumptions. You can't have a theorem about whether or not that is the minimum.
I guess my only question would be, why do people want high dimension?
It's a lot of high dimensional.
Well, no,
Flippant, but it is. I mean, all of these problems that people want to solve in the main space, they tend to be high dimensional. So maybe what a couple of people talk about, which is perhaps like a bit more, is actually just try and split it out a little bit and do approximate problems with models which aren't directly the real thing, but seek to approximate.
I think what's very appealing is the idea of the kitchen sink approach, that I mean, this is almost toward somebody quoted the n equal all baloney. But the other sort of fantasy is like, I'll just throw in all the data and all the possible parameters of interest and let the algorithm sort it out, or let the model sort it out. And that's not generally a recipe for success. I mean, if you think about it, it kind of violates the no free lunch theorem, among other things. But I think that we're fortunate that in many scenarios, the underlying structures are much lower dimensional than the data sets would suggest. It's just that sometimes we have to go through a fairly complex process of model building and understanding to figure out how to tease out the right low-dimensional structure. And again, I would suspect that that's a feature of common problems. I mean, it's a little bit what I think Giles alluded to this as well. Another way to think about it is the kind of the Google principle, which is like more data beats clever algorithms, right? I mean, there's a lot to be said for, I mean, this is only true when the data aren't too heterogeneous, but simple, robust procedures can do well when data are in abundance. When data are rare or expensive or heterogeneous or poor quality, it's always going to require, I think, more work to tease out an answer. And one last comment on that was one of the trends that we're seeing emerging in academic statistics, which also featured in this morning's talk because it's part of a theme of the conference, is a more explicit understanding of the trade-offs between computational efficiency and statistical efficiency, which has a genuinely good definition if you think about sampling and, you know, what's the smallest sample size you would need to get a certain level of error bar and so on and so forth. So the notion of statistical efficiency is well defined and it's been understood for a long time, but the choice to study procedures that allow one to trade off between statistical efficiency on one hand and computational efficiency on the other that's starting to become an important topic of research. And I think again, that Giles alluded to this point, that's also becoming, it's often necessary in practical applications. One has to trade off time, I mean, you know, it's the usual size, weight, power, et cetera. All these types of trade-offs have to be made in any practical problem. And so that's something we're seeing more and more of. I don't know, anybody else want to add to any of that?
I make one point, which is about a lot. It's very easy to look at a lot of the everyday examples of big data that we come across, and from this try to generalize too much. And one of the classic things is all of the online stuff we see today, there's an absolutely critical point in terms of the system, and that is in nearly all of these, there's a human in the loop. So when you do search, it's not some marvelous search algorithm. PageRank, I mean, there's thousands of algorithms that were just as good as PageRank. Number one, it's the fact that you as a human being have put in data every time you use it. And when you see 10 things, you are making the decision. It's giving you here's a guess at the things you might want, but it's your input. And the decision process there is the human being. The same with Amazon recommending things. It does keep trying to sell me another lathe. I don't need another lathe. It's still trying to sell it to me.
What did you buy before?
Did you need Santa Claus bought me a lathe? But there's a human in the loop in these, and I think there's a real difference when we look at a lot of the examples that are held up as this is brilliant data science. Actually, the data science may not be terribly good, and the statistics may not be terribly good, because there's a human at the end of the day making a decision. Whereas when it's a predictive algorithm that's going to do something automatically, and we've seen the examples of where that can go wrong, then you have to be a lot more sensitive. That gets back to this issue of being able to understand what the statistics, what the model is that's actually being represented. What is it that you're actually representing by the statistics? Whereas those eigenvectors of optical character recognition that I see in the papers, you look at them and you go, why? You know, why does that distinguish an A from a B? And when we're dealing, so again, it comes back to my issue with humans. When we're dealing with human data, you have to be able to explain to someone why this has happened. The example I gave, and Rolls-Royce would have this example as well. If you learn some model about how this engine works from the data and you have no interpretation of it in terms of physics, engineering, and chemistry, you're going to be a bit wary before you deploy that. And you have to think twice before you use the data model to just drive that autonomous vehicle. I'm going to make it in public.
Yeah, so I don't want to cut in too much to our half an hour of networking time. So let me thank again all the speakers from this afternoon. Thank you.